Good morning. I'm Courtney Carr, Director of Marketing and Education for CAPSA. Thank you for joining today's e-training webinar, How Copper Strip is Rolled, Tested, and Used, presented by Julie Junot from Revere Copper. Julie is the Quality Manager at Revere Copper Products. She is responsible for managing the process engineering team, document control, and the lab. She has been at Revere for 19 years and held many positions. She was hired as a process engineer in the rolling mill, transitioned to the lean team where she facilitated the implementation of lean principles within the organization. After that, she became a work cell manager and was promoted to superintendent of the rolling mill. She served as the production control manager before assuming her current role. Julie holds a bachelor's degree in chemical engineering from Clarkson University and a master's in executive human resource management from Cornell University. During the presentation, you may submit questions into the Questions tab on your webinar toolbar, and we will answer them at the conclusion of the presentation. Following the webinar, you will receive a link to a survey. Once you have completed the survey, there will be a link to download the presentation slides. You will also receive a recording of today's webinar. Feel free to share the recording and slides with others in your office. With that, I would now like to turn the presentation over to Julie.
Good morning. I'm going to go right into it. So let's start out. This is how copper strip is rolled, tested, and used. So first, what's special about copper? Why is copper so widely used? So copper is highly available, highly recyclable, it's pretty, corrosion resistant, antimicrobial properties. It's an excellent conductor of electricity, an excellent heat transfer, has great jointability. It's also easily alloyed. So why does copper have all these special properties? So you got to go back to like high school chemistry here and the periodic table of elements. And copper is in the same product family as silver and gold. So what does that mean? That means that copper, silver, and gold are going to have some similar properties, whereas aluminum, which is number 13, that's one that's commonly substituted for copper. It's going to be a little bit different. And same with iron, a metal everybody's heard of, Fe, so that's number 26. So what are those properties and how do they compare? So we're going to start with the atomic structure of copper. So you don't have to know a lot about copper and the atomic structure to understand that the key thing is that outer layer of the outer electron layer, the outer shell. There's one electron in that outer shell, and that is the same in gold and silver. And that one electron gives it a lot of those properties that make it similar to gold and silver as far as reactivity and conductivity. So here's kind of a comparison. You can see the electrical conductivity of silver at 105, copper at 100, gold at 70. Those three are pretty close. And there's a significant drop when you get into aluminum and go all the way down to iron is down at 17%. And then thermal conductivity, you'll see copper also very similar to gold and silver. And then you see a drop for aluminum and then all the way down to iron. And so what makes up all those properties? So we're going to dive deep down into the microstructure of copper. So all solid metallic materials are crystalline in structure. And with copper, it is in a structure called face-centered cubic. So if you look at that picture, you can see that those black dots represent copper, or represent atoms in the crystalline structure. And the black dots in the center of the face are what make it face-centered cubic. Now that crystalline structure determines its physical properties. And the face-centered cubic elements tend to have better ductility and better malleability. Silver and gold also fall in there. So if you look at copper under a microscope, you can see those crystals. And each of those crystals is called a grain, and the boundaries between them are grain boundaries. So the top picture actually shows a billet that was cast, and it freezes toward the middle, and the grains grow toward that freeze point. So the grains are elongated towards the middle. And then the second picture is more closely resembles copper that's been rolled or cold worked and annealed. So in that case, the grains don't have directionality. The ability of metal to be worked is based on this crystalline structure, so what you can do to it, what it's capable of. So what can you do and what can you measure with copper? With copper, you can measure the ductility, which is measured by yield strength and elongation, strength, which is measured with tensile strength, the hardness, and then it also has electrical conductivity. So customers look for different properties depending on end use. Obviously, conductivity would be really important in electrical applications, but if it was going to be drawn into, let's say, a deep bowl shape, ductility and elongation would be extremely important. Or if it was going to be used as a structural support, you'd want high tensile strength. Now, you can get all of those properties from copper depending on how you cold work it. So how are those properties developed? So cold work is basically doing any work to the metal while it's cold. And what happens is those crystals are deformed and it causes stress and it raises the tensile strength or hardness. So some examples of cold work are rolling, drawing, or hammering. So what happens to the metal? So as a result of rolling, the grain assumes a preferred orientation. It becomes longer. I'll get a picture here. And due to the stress and defects that are put on that crystalline structure, the material becomes harder. And so that's also called tempering. You've tempered the material by cold rolling. So you can see when it's first going into that first set of rolls, the grains are big and they're non-directional. And then as you roll it, the grains get smaller and squished and elongated and they become directional. So I have a picture of what that would look like under a microscope. So that first picture more closely resembles that picture I showed earlier of the structure after it's been maybe cold rolled and annealed. So you've got good grains, good grain structure. You can see it. There's not a lot of directionality. Then as you start to do a reduction through rolling, those grains get squished. They start to get elongated and directional. And eventually, they almost get smeared out. You can barely see the grains in the last picture. And that's after quite a bit of cold rolling, it would look like that. So little slide on what cold rolling is. So we have many configurations for rolling mills. This would be a 2-high configuration. So in this case, you've got 2 big rolls that are putting pressure on the metal, which runs through the middle and does a gauge reduction. There's 3-high rolling. In that case, the metal is going in 2 directions. So it goes and it turns around a point and comes back, and you're rolling it 2 directions at the same time. A 4-high mill. Now in this case, you've got the green rolls on the outside are really just to supply tonnage or force, and your work rolls in the middle give it its surface. And then there's also a cluster mill design or a Zensemeyer mill. And with the cluster mill, you've got a lot of rolls. You've got dry rolls and bearing rolls, and those tiny rolls in the middle are your work rolls. The cluster mill gives you some better gauge control usually and some better shape control than some of your other mills. So what happens to the metal mechanically while you're rolling it? So as we mentioned earlier, you make it stronger. You add strength to it by deforming those crystals. So that top slide shows an increase in tensile strength as you reduce the thickness. So let's say you started with a piece of copper that was a 1/2 inch thick roll of it, and you rolled it down to a 1/4 inch. You did a 50% reduction. Your tensile strength would go from about 200 up to, it looks like about 350. And then your elongation at the same time is going to go down. So that's your ductility. So as the metal gets harder, it becomes less ductile. So at the same reduction, if you went from a 1/2 inch to a 1/4 inch, your elongation will go from 40% down to about 50%, or down to about almost nothing. So strength increases with cold work, and ductility decreases with cold work. That's really the takeaway from that. Now, when a customer orders copper, they're looking for certain properties. So if they wanted both strength and ductility, they would have to order something that's got some cold work to it, but it's not full hard. So for example, like a roofing copper would be ordered generally at quarter hard, because you want the hardness, you want it to be resistant to dents if it's going to go on the roof, but you need it ductile enough to be able to form the seam. So this is an example of different hardnesses for hard metal that's ordered, and it's the key to getting that property is a % reduction in thickness after the last anneal. So, back to my other example where I did a 50% reduction, that would be extra hard on this chart. So if you look at extra hard, and you went from a 1/2 inch and you rolled it to a 1/4 inch, you would have a 50% reduction, and your tensile strength would be 47 to 56, and it would be designated as extra hard, or HO6. And this chart kind of shows you all the different options that you can order metal through, and this is the ASTM standard. So now I mentioned that your hardness is dependent on the reduction after the last anneal. So what is annealing? So annealing is basically a reset for the metal. You can't just roll and roll and roll, because it gets harder and harder and harder, and you get to a point where it takes too much force to do the reduction. So you anneal it. So let's say I gave that example of a 1/2 inch down to a 1/4 inch. Well, let's say your metal starts at a 1/2 inch, but you want to order it at 0.01 gauge. You might not be able to roll it from a 1/2 inch down to 0.01. It would get too hard. So you have to have a reset at some point in there, which is what annealing does. So with annealing, the metal is heated above its recrystallization temperature. Stored energy plus heat energy forms new grains, so those grains grow again, and those new grains are capable of absorbing more cold work. So now you can roll it down further. So the grain size depends on time, temperature, the cold work done previous to the anneal, and if there was an anneal done previously, and also the chemistry, how pure it is, if your copper is 100% copper, or if there's impurities in it. Metal can be ordered soft, and when it's ordered soft, it's annealed as a final step. And when metal is ordered soft, frequently it's ordered to a certain grain size. So there'll be a little bit more about that moving forward. So just a little bit more about annealing. This graph shows the hardness versus annealing temperature if it's annealed for 30 minutes with 60% prior cold work. So if you think back to that other chart I showed, 60% means it was spring hard, or HO8, and then it was annealed for 30 minutes. And you can see that at 600 degrees, you start getting grain growth. At 400 degrees, you have recrystallization happening. So depending on how much grain growth a customer wanted, that would be determined by the temperature, and then also time. So this next slide shows a little bit about time considerations with annealing. So you can go with a lower temperature and a longer time. Basically, higher temperatures shorten anneal time, or lower temperatures, you have to go for a longer time. And that's for grain growth. So if you were going to order soft metal, what would you see from different grains? So some considerations of grain size. So the first one is strength. So fine grains result in lower elongation and higher mechanical properties. So that would be if you annealed it just so that it have recrystallization but not much grain growth, you can get stronger copper but it's not going to have the ductility or the elongation. So directionality occurs when metal is cold worked in one direction. So we create directionality when we roll it. Then when we anneal it, you're trying to remove some of that directionality when you're growing your grains. So depending on the grain size, you will retain some directionality. So if you wanted big grains, you can remove that directionality, but little grains, you might retain some of that. So you might have stronger metal that's got some directionality. Formability kind of goes along with the strength. It's kind of the opposite. The larger the grains, the fewer the boundaries, the greater the potential for deformation. So that just means you can pull it deeper, make a bigger bowl or a deeper draw on it if it's got larger grains. And then the more grains it has, the less it will draw. And then finally, surface. So there's a condition called orange peel, and if you do a lot of cold work to metal prior to annealing, and then you anneal it to the point of a lot of large grain growth, large grain structure, you can get a surface that looks like orange peel. Whereas if you anneal it for a shorter amount of time or a lower temperature, you'll have a smoother surface. It'll give you more of a cold work looking surface if you have fine grains. So I'm going to put that all together for you, a lot of information to process into basically what do you do when we're rolling metal. So we cast these cake. They're also called ingots in the market, and they are 6 3/4 inches thick, and they're black on the outside. That's an oxide that forms, and that has to do with the copper being highly reactive, and it's heated to 1700 degrees for 2.5 hours. So this particular cake was 6 3/4 inches thick, 26 inches wide, and 25 feet long. So now it gets rolled, and it gets rolled from that 6 3/4 inches thick down to 0.55, which is a little bit more than 1/2 inch. But this work is all being done while the metal is hot. So this is not cold work. So when this metal comes out as a coil that's about 1/2 inch thick, it's in that reset condition. It's basically been annealed. It doesn't have directionality, it's got big grains, and it's ready for processing. The first step is an overhaul process, and that's because when you heat the metal, you get oxide. So those cake were black. As this coil, once it's rolled at 1/2 inch thick, it will be black. It'll have oxide on both sides of it. So the first step is to remove that oxide. So that's milled. So it's physically scraped off and removed. So there isn't any squishing of the metal or cold work of the metal there. So again, you don't have any cold work between 550 and 505. But then our next step, this is where the cold work starts. We roll it to 0.370. So we take that metal and we roll it down further, depending on the order and the final gauge. And I'm running through an example here. I'll show you what we're headed to in a minute. So the next step is we continue to cold work it from 370 down to 090. So that's a 75% reduction. That's a lot of cold work. So this metal is going to be extremely hard at this point. We can continue to roll that metal. And in this example, we roll it down to 0.042. So now we haven't had any anneals since that 0.505 gauge. And it's very, very hard metal. So for this example, we're trying to make 0295 gauge, and I'm going to show you soft on the left side and 3/4 hard on the right. So the next step is to anneal it. It's gotten extremely hard, and basically we need to anneal it to continue with the reduction. But that 0.042 isn't a random gauge. We didn't just roll it from 090 to 0.042 because that's as far as we could go. What we're looking for is, in order to get that 3/4 hard reduction on the right-hand side, you have to roll it, you have to do a gauge reduction of 29%. So if you want the metal 3/4 hard, you have to reduce it 29%. So to go to 0.0295, the 29% reduction, you have to start at 0.042 after the last anneal. So we get it down to 0.42 and we anneal it. Now on the left-hand side, it's soft. You can see we annealed it slightly slower at 45 feet per minute versus the right at 55. That's because we're looking for soft properties at the end of that example. So then the next step would be to finish the gauge. So it's going to get rolled again, and this is cold rolled. And on the left side and the right side, you're going from 0.42 to 0.295. On the right side, it's done. It's at its final gauge, and we send it to the lab for testing to make sure it meets its temper requirements. On the left side, it still needs to be annealed again because this was ordered soft. And in that case, it's annealed at 70 feet per minute, so much slower. And that is to hit a certain grain size. And depending on what grain size was ordered, you might range that from 50 feet per minute up to 100 feet per minute. And the operators are actually cutting samples right there and checking the grain, and they can speed or slow down the machine as needed. But we've got that pretty well dialed in as to what speed they need per grain size. Then they would both get cleaned with acid and soap and anti-stain. They'd get slit to their final width, packed and shipped out the door. So before that metal gets shipped, we take the lab sample. And so I want to go through a couple of test methods that we do. The first thing, we always test for chemistry. I mentioned earlier, it's got to be pure. There's an ASTM standard that states what the purity level needs to be, but it has to be pure in order to meet those properties for the anneals to work and for the rolls to work. So we do a spectrochemical analysis to make sure that copper meets requirements. Then we do tensile testing. So with tensile testing, we're testing for yield, elongation, tensile, and then there's actually others that can be determined through this test. Again, ductility is your yield and elongation. And how do we do that? We take a sample of that metal at its finished gauge and temper, and we cut it into this dog bone shape. And then that gets turned vertically and put in the machine that's pictured to the right, and we pull on it on both ends. And this graph represents what the machine gives us for information that if you look at the graph, the yield strength point is the point where you are beyond elastic deformation. So it's a point where the material is permanently deformed. It's not going to go back into place. Then as you kind of follow that graph, the ultimate tensile strength is the most force that gets applied prior to breakage. And those are results that get reported with our product. Hardness testing, if a customer asks for the hardness, we do a Rockwell hardness test. There's other types of tests, different scales, but within the Rockwell, there's the 15T, 30T, F, and B. Those are dependent on the gauge of the material. So you can't apply the same amount of force to a really thin gauge as you can to a thicker gauge. So that's the difference in the scale there. We also do a ductility test. That's just to confirm that it meets the properties required for being deep drawn. This would be for metal that's ordered soft. And also for soft metal, we'll do a grain size measurement. And with the grain size, we're basically looking at it under a microscope, and the average size is reported in millimeters. So what does this product get used for? Copper strip. We have a lot of markets. Our major market is architectural, and this is an example of Freedom Gray. So this is copper that's got a zinc tin coating on it, and this is the Denver Capitol building. This here is a picture of it's also Freedom Gray. This is the Museum of the Bible in Washington. And you can see that's got a unique curved shape to it. You've got to get the properties that will curve and still look flat and be able to create that seam as you're bending it. This one is the Bethel Woods Center for the Arts. This is in Woodstock, New York, and this is where the original Woodstock took place. And this is bare copper. Other major markets, electrical. Bus bar used in electrical panels, or transformers. And then finally, another major market for us is HVAC. And what that is it is refrigeration units on cargo ships. And that is the end. So I'm going to open it up to questions.
Thank you, Julie. As a reminder, please submit any questions using your webinar toolbar. We'll give it a minute or so while you type your questions. While we're waiting for questions to be typed out, I will remind you that you will receive a survey about today's presentation. Once you complete the survey, on the second page it says thank you, there will be a link to download the presentation slides. And then tomorrow, in a separate email, you will also receive a recording of today's presentation. Maybe 30 more seconds to see if any questions come in. Okay, we'll go ahead and wrap our presentation up. If you have any questions, please feel free to reach out to CAPSA or Revere. We'll be more than happy to answer them or pass them along. Thank you all for attending, and I hope you have a great rest of your week.